Hi. Yeah. Thanks for showing up. I know it's early for me, and it must be early for my and my colleagues as well. At least some of them. It's a great pleasure for me and the colloquium committee to welcome Professor Maria Gini from the University of Minnesota. It's cold for us, but it's kind of hot for her here already because it's in the mid-40s. I have known Maria for maybe 20-ish years or so when we were at the start of the autonomous agents and multi-agent systems community. So in that community, it's good to point out. So at the time, AI had gone off and done lots of work in specialized areas like natural language and machine learning and knowledge representation. And we had this community come together to pull things together, to bring in the human element, to talk about how to build a complete intelligent agent that could also work with other intelligent agents and form multi-agent systems. So now, 20-odd years on, AI has again had many breakthroughs in machine learning and natural language. And once again, people are interested in how to pull things together. And that and the advances in AI and robotics bring up the need for how to have intelligent entities that can interact. And this is what Maria has been doing for much of her career. And most recently, she's been working on the problems of systems of agents, systems of robots in particular, that she's interested in. And she's going to be talking about some of those things today. Maria is an extremely well-known researcher. So she's had any number of awards. I can mention a few that I can remember. So there's she's a fellow of the IEEE, fellow of the AAAI, fellow of the ACM. She won the SIG AI Autonomous Agents Award. And that's just for research that I remember. She's also won multiple awards for mentoring. So she won the Harold Notkin Award for mentoring. She most recently won the presidential, I forget the full name, the Presidential Award for mentoring in science engineering.
Yeah, it's a funny name.
Very long name, but very prestigious and difficult award to get. She's also won service award. She's been chair of the ACM SIG on AI. The interesting thing with Maria is, and this is a good advice for the students here, that you can do well by doing good. Be nice to people, and it actually is a good strategy for life. So with that, let me turn it over to Maria to tell us about her research.
Okay. So thank you for the nice introduction. You also got the Autonomous Agent Awards, right? The same thing. So you also have a lot of awards. So I always like to recognize. So, okay. It's really an honor. Oops, sorry. There's a problem in the microphone. So I need to do something. Okay. So it's an honor to be here. And what I decided to do, since we're all researchers, right? So we all love research. So I say, instead of telling you what I've done for many years, it's already published, so you can read it. I try to pick up a new topic, something which I just started doing some work, so I don't have a lot of results. But what I'm hoping is to get enough of you to think about, wow, can I trust my teammates? Are they friends or foes? It's kind of a topic that is coming up in the community. So just a little bit of history. Now, I've been in computer science for a very, very long time. Many of you are younger, so you've not seen the early days. But one thing that is very common in the computer science community, early days, there were no passwords. Why would anybody want to come to my computers, right? What's the reason? Why do we need to protect things? And I still remember I was at the AI lab as a postdoc, and the AI lab at the time, again, this we're talking about 50 years ago, right? So a long time ago. So they had a system in which they had a giant disk that was storing all the information for all the TV monitors that people were using. And so you could sit at your computer and click a button and see the screen from somebody else. Again, no password, nothing, no privacy, nobody was complaining. And I just, remember the past. At the time, John McCarthy was the director of the lab, Hans Moravec was there, and both of them were playing one of the very early games. And so they were protecting their screen from each other. There was a way you could hide your screen, so they couldn't see that the other one was doing better, right? Because John McCarthy and Hans Moravec were playing, oh, I did this, no, I did that. So again, but the idea there is, you don't need to, everybody's friend, so you don't need to cover anything up. And again, if you think about it, passwords, again, started being common much, much later. Again, all of you now use password everywhere, do authentication, all this stuff. It didn't used to be. And I think, again, the computer science community, maybe we were a bit naive, the early days, but assuming everybody is a friend. Nobody wants to do any damage to me, right? And so again, think about even cybersecurity, which now everybody talks about, there are degree programs and so on, didn't exist until finally somebody said, people can get into my system, steal my data, attack my system. Why would anybody be so bad to do it? And I think, again, and I like it, as a community, I think it's a good attitude to have. But at the same time, now we have to be a little careful, because if you are too nice, then we have to pay a price, right? And so the question now here is, are we sure that everyone is a friend? And maybe it's not. Now, in the specific case of agents, or we call embodied agents, which could be robots, there are a few other issues that often comes into the picture. Now, again, the main assumption is that robots are a friend to each other, agents are friend to each other, they're not malice, they're not going to damage anything. And this, again, has been for a long time. The distributed AI, which was the early term before the multi-agent system conference came into the picture, again, they were looking multiple agents, no central control, each one does whatever they want, and there's no damage done. Wow, isn't it cool? Isn't it like, again, you're a collection of friends? But same thing happens in swarm robotics. Swarm robotics is an area of robotics which hasn't really produced any real results, in the sense applicable results, but there's a lot of papers. As you kind of know, right? In academia, we come up with crazy ideas, and then many, many years later, someone says, oh, yeah, those are good, those are useful, right? So swarm robotics is still at that stage. You say, oh, I can have, thousands of robots, So I have let's say there was a concert in a park in Minneapolis, that's where I come from, and after the concert, there's a lot of garbage, right? People drop stuff. So now I have my swarm of robots, and I say, go and clean it up, right? And my robots go around, pick it up, and they don't need to be told exactly what to do. Each one say, oh, I see a piece of paper here, I'll pick it up, right? So this is kind of your swarm robotics. No central controller. Each one knows what to do, and they try to do without running into each other, right? In practice, this doesn't work yet. And one of the reasons also is because if you have no centralized controller, you really have to be very careful. Make sure that your robots are all your good robots, right? Suppose, I won this, there's a competition, say, okay, I need this amount of money to send my robots there. Suppose that another company wanted the same thing, but they didn't win the bid. Now they can send their robot to mix with my robots. And instead of picking up the trash, they dump it, right? It's possible, right? No centralized control. I assume all my robots are good, they do what they're told to do, but who knows, there may be another robot that does something else. And so we really have to start thinking about a little more carefully, is everybody really a friend or not? And with physical robots, there is another issue, that often there are failures, sensor failures, mechanical failures, battery failures, which could look at some level like is an enemy or is a lazy robot, right? You can say, this robot sits there and didn't pick up anything. Is this an enemy? Is this, again, my other company, they send robots just to stay there and prevent me from moving? Or maybe the poor robot doesn't move because the battery is gone, right? And so also, sometimes, again, robots can look like they're not doing their work because of physical issues, again, sensing issues or so. So again, we kind of have to be able to, as much as possible, to kind of assess and understand, what the system can do. So this brings up, this is a lot of text here. This brings up the issue. If I want to check what other robots or agents do, we need to think about trust. Trust is one of those wonderful words that we use all the time. So we kind of know or think everybody is exactly the same notion of trust. But the question is, can we somehow make it more specific and apply to autonomous agents? So there was a kind of a very interesting paper a long time ago by two I'm Italian, by the way, in case you don't recognize from my accent. So there were two Italian fellows, Cristiano Castelfranchi and Rino Falcone, who wrote many, many years ago a paper which is very well known in the agents community on trust. And they started talking about trust. And trust has many, many, many dimensions. So I'm not saying here I cover all the aspects. There are many, many more that I'm not going to touch. But the issue they were talking at the time is try to distinguish or connect trust and control. Because you can think about control as being kind of opposite of trust, or they can be things that collaborate in some sense with each other. And so again, what they were arguing there is that trust is not a binary state, but it's kind of an evolving factor, which is essential for collaboration and decentralized systems. So this paper, again, is a very, very old paper, kind of open up in the agents community the notion. Again, maybe you need to think about trust and how we're going to think about trust. Now, trust, again, is typically developed through repeated interactions. Again, if you think about human communities, if you are in a team, with your company or a team with other students or whatever, colleagues, if you're in a team in general, trust develops over repeated interactions. And, as humans, we always assess each other. Right? Even maybe implicitly, we don't intentionally say, do I have to look, is my person here, my colleague here, should I trust him or her or not? But takes some kind of time and is assessed kind of in a continuous way, right? So I could have, again, a colleague and I trust, and I say, okay, can you help me? Can we do this? And then maybe after a while, did you do? Oh, no, I was busy. Okay, so, the trust evolves. It's not, I trust one person forever. It's like I give you a stamp, right? In some cases, yes, friends are real people that we trust all the time. But in other cases, again, I have to adjust. I cannot, again, assume I trust it once and it's on forever. And when you have decentralized systems, again, trust mechanism can be useful. Will be useful because they can help make the agents make informed decisions and reduce the potential for exploitation. So I'm personally interested, of course, human trust is very important. There are experts here, I know, that know much more than I do. But I'm kind of a computer science, maybe old-fashioned. I like autonomy. I like, my robots or my program, do this, and then I can go and do something else. I like to trust them, let them do things. And humans, we are very complex, right? There's a lot of work now in AI community, right? Human-robot interaction, human-systems interaction. And it's difficult because humans, again, we are difficult, right? So an autonomous system is simpler. I can kind of control it much better. So again, my work really focuses on autonomy, and I leave people out. Not that they're not important. I hope some of you are really interested in working with humans and figure out, again, combine, issues of trust. Now you have a human and some robots or some agents, right? I'm not saying it's not important. It's just not the kind of things that I know enough about. And so again, I stick to my old-fashioned autonomy, which is, one of the very early ideas in the AI community, right? You want to be a system that can do things and I can trust them. And so, trust is kind of important, again, because will foster collaborations, can reduce uncertainty, and has a lot of nice properties that we like to have. So, before we get to talking more in details about trust, there is one important issue. The assumption that we often make in computer science is that agents are rational. Anybody who writes or uses the Russell and Norvig AI textbook, which everybody in the world uses for the AI classes. Kind of see there is a chapter 2. I teach this class all the time, so I can see the pictures. I have this picture of a kind of a sort of robots with legs and a head that interacts with the environment. And they define a notion of rationality, which is an important way of defining something that is quantifiable as opposed to talk about intelligence, right? So the big debate in the AI community is how do we define intelligence? And intelligence is too difficult to define precisely. Rationality you can define formally and precisely. Right? And so talk about the rationality in the sense that we want the agent to be rational and have some kind of objective. And typically there are different kind of rationalities, and it could be self-interested agents or cooperative agents. And rationality, basically, you have some kind of utility function that is given by the outside, and that's what I try to maximize. Again, I don't know if you have, how many of you have used the Russell and Norvig book? There is an example there. See, I teach an undergraduate class. And there's an example of a vacuum cleaner that has just 2 squares to clean, right? And the example is very simple. So if the external function that you're trying to optimize is try to get squares cleaned as many as possible and do a number of steps, what ends up, again, I don't know if you've seen, if you're not seen, maybe it doesn't make sense. I use it every time I teach AI, and every time students, oh, but this is stupid. No, it's not stupid, it's rational because I told the robot what to do, right? And it's a very important distinction because, you know, if my objective function that I give to my robots looks stupid, so if you have this vacuum cleaner that goes back and forth for 1,000 steps, is it clean? Yeah, no memory. Is it clean? And it goes on back. And you say, it's stupid. No, it's rational. That's what I told him to do, right? So it's very important kind of thing to keep the distinction. And again, the rational agents try to maximize the utility. So the question is, why not just say maximize the utility and forget about everything else? So now this kind of opens up a little bit, and I'm not spending a lot of time here, but just to get slightly broader in the issue between trust and cooperation. So trust typically enables cooperation, right? You cooperate if you trust people. And why is important in cooperation? Now this again, get a little bit of broader issues. You know, when you do positive interactions in a society, you have a positive sum, something comes out, which benefits the entire society. And if you think again about human societies, cooperation really, even animal societies, right? The cooperation is really a foundation to increase the good for everybody. And so trust enables cooperation. And what is interesting, cooperation also requires trust. So they're kind of those two concepts. And again, there are many other pairwise concepts that we could use. The cooperation and trust are kind of connected to each other. So trust is valuable, but I have to trust my partners. And again, both partners have to be worth of trust. Otherwise, if I trust my partner and the other partner doesn't trust me, then we have an imbalance. And anytime there is kind of violation of trust, decreases future cooperation, right? If I work with one of you and I trust you and then you fail, don't deliver, then future cooperation, I will not cooperate with you anymore, right? And unfortunately, sometimes the robots or agents don't have a choice. But again, you know, again, this notion that cooperation and trust are kind of connected to each other. And so then the question is, how do we build trustworthy AI? And again, human societies have a lot of ways of doing this. I'm not an expert in human societies, human trust, so I just kind of mention this. But of course, if you want to understand trust, we can study human societies. So it's very important. Again, it's not what I'm doing. You know, as a researcher, we don't do everything, right? I mean, for the student here, don't try to cover the entire world. Pick up your slice, your piece, and focus on that so you can make contribution. So again, looking at how human societies develop trust and so really can help in getting better understanding of what we can do in agents, but it's not everybody is to do it, right? So again, there is a lot of papers on human trust, regulation, punishment. Punishment is another very interesting concept that is used in human societies, right? If I trust you and you do something improper, then there will be a punishment. Now, if you have a robot, how do you punish a robot? No battery power? Does a robot care? right? So the notion of punishment, again, is very important in human societies, but it doesn't really affect autonomous systems. So you have to think about something else. And so one of the key ideas, and this is Ben Kuipers just giving a talk recently at the III conference, that we need to kind of consider trust as what he calls a capital asset, because it's a necessary thing to do, and must be included, that's what Ben Kuipers' opinion, in the utility function. So in the utility function that I give to my agents, I have to include some notion of trust. So trust impacts the utility function. And then again, in ethics really is teach how to be trustworthy. Okay. So again, I'm just trying to give a little bit general context so you can kind of see where things comes from. Now, let's get to the kind of things I tend to do, which is, write software, use robots, and build systems, right? So there is, after the paper by Castelfranchi, people started looking into how can we make computational issues of the notion of trust. Again, Castelfranchi and Falcone describe trust, many different ideas, but there's no implementation. So there was this group, and here I put the citation, it's a very old paper, and then they started building a system which they call TRAVERS, which is kind of framework for agents to do trust assessment in multi-agent systems when the agents interact directly with each other. And it's a system that allows for the agent to assess how the other agents are worth of trustworthy, by observing what they do. And again, think about it, the ideas here came really more from human system. Again, I work in a team with other people. I look at what other people do, and I make my assessment. And the assessment is not fixed in a sense, maybe I trust one teammate, and then I get some defect, and I will never trust the person again. But sometimes, okay, yeah, you didn't do well this, but I can still trust you, and maybe the trust is something that can go up and down over time. And so TRAVERS, this system, creates kind of a system. I'll go through a couple of equations just to give you a little bit of intuition of what they're doing, in which, again, you have this agents evaluate each other depending on how reliable are and how consistent they are in real time. And this, again, evolves over real time. Just to get a little more specific here, the trust model, again, that is using TRAVERS. TRAVERS, again, is not my system, again, it's old system on which you're just building now. So the trust, so we think trust is kind of pairwise. So it is a trustor and a trustee. So the trustor estimates the probability that the trustees will fulfill its obligation during the interaction. Okay? So I'm a trustor, I have a trustee, and I estimate how likely is the trustees will fulfill whatever the obligations are, whatever the trustees have been told to do. And the confidence basically is a metric that measures the accuracy of the trust value that's computed by the agents. And the issue here is how is this trust value computed so that then can be used to do all the calculations. And in a short term, the expected value of the probability that the trustee fulfills his obligation is expressed, now we get into a little more technical terms, using the beta family of probability density functions. Doesn't mean that that's the only choice, but this is a choice that they made, right? And so just the beta family of functions is a distribution that is characterized by two parameters, which are called alpha and beta. Just show here a very simple example. That's kind of the foundation that is used in the trust models. And now, again, I'm trying to write a few equations just to give you a little bit of intuition without getting into too many details. So the trust model, again, using these beta functions, I have to specify the values alpha and beta, so two parameters that affect the shape of the function. And alpha is used to represent the count of positive interactions. So interactions say, yes, you've done your job. And beta, the negative interactions, right? So the expected value of trust between two agents, again, the trust is always pairwise. Of course, if there are many agents, I will have multiple pairs, right? And it gets a little more complicated, but it's always from a pair. So the expected value of trust is expressed as, again, express the expected value, the trust between I and J, which are my two agents, and it's this very, very simple formula. At the end, you think about all the details. At the end, I have alpha divided alpha plus beta. Again, alpha is positive interaction and beta is negative interactions. And so the trust value then is this expected value given the observations. And so the trust value has to be computed at each step because each step make a different observation. And then the trust value, again, is this expected value given the observation. Okay? So again, just to walk you a little bit so you have a slightly better understanding of how this works. So if I have an interaction, so there are a lot of interactions over time. If I have an interaction, if it's successful, so I say, yes, you're trustworthy, I get a value 1, otherwise get a value 0, and then the alpha value is updated, and the beta value is updated. So at this step, either I trust or I don't trust, the interaction is positive or is negative, and the alpha and beta values are changed. Right? Very simple way. Now, this is, so the work that I described so far, again, in very short terms, is what happens, again, in this system, Travels, which, again, is the first system built on these ways of measuring trust, and this alpha and beta. Very simple idea. It's kind of, I like when things are simple. They're not too complex. And it's been used in different number of applications. But now, so we started working with one of my students because, again, I got fascinated by this idea of trust. So again, hope some of you will get fascinated and will do the real work, right? Because I'm not telling you, oh, that's what I've done, just copy, read what I've done, read my paper, cite my paper. Forget about it. Think about yourself, what you can do, right? This is a very open research area, and for PhD students or any student who does research, of course, even faculty. But if you're a student, you want to get research in an area where there's not too much work already done, right? There are kind of two styles if you want to do research. You take an existing area and you change the epsilon, small things. Oh, this is my contribution. That's okay. Or you take an area open. You can wander. You can do lots of different things. Very few people have worked in this area. I personally like this open space. I don't like to be, channeling and narrow things, but, it's styles of work that people have, different styles. So again, the reason, again, why I try to talk about this is to convince this is a very important area, very good area. There are some papers, not too many, so you have more space to come up with your own ideas and produce something, novel and interesting, which at the end of the day, if you want your PhD, that's what you need, right? You can do lots of work, but if it's not novel, your advisor is going to, not good enough, not yet there, right? So again, I highly recommend. So what we did, again, this is one of my students, so we decided that trust, the way it's done in the Travels, is kind of binary. Either I trust you or not. And maybe we can make more refined. I'm not saying that this idea is a perfect idea. We're still working on. Again, I show some initial results, but we may end up changing something. So we decided, often the other agent can have different types. It's not always that I cannot trust end of the story. Maybe I have an agent which is lazy, so it doesn't. It does the work, but it's kind of slow. I can have an agent that really adversarial. So this is kind of more danger. I can have agents that kind of mix into different things. So what we do is extended the notion of trust, the alpha and beta values. And now we keep separate alpha values and beta values for the different types of agents, right? So again, if it's adversarials or if it's lazy, so we keep separate values. So instead of having a single trust value, I have different trust values. And of course, we use the variance to quantify what is the uncertainty of the knowledge that I have. And then we can again measure the probability. Now we have multiple types for the agents because it's not just one type. So again, we have this type of the agent, and again, we use our beta functions like same way, and everything is updated in a very similar way, except again, we have multiple values, right? So I think I can skip this. I'm trying to keep track of time because I want to have time for question and discussion, right? That's what I like. So this is kind of summarize a few equations. I think I can skip this. Okay, so now let's look at the specific case studies we worked on. Again, I hope some of you will do better, right? This is by no means is the perfect work, right? I mean, as you know, when you do research, you start, some ideas, things evolve over time. That's the beauty of research, right? You're discovering something new. So again, what we kind of look at is have trust matrix, as we talked before, in which, again, there are different types of agents, and then we use kind of Bayesian game theoretic approach to enable an agent that does reinforcement learning to interact and build up what the trust value of another agent. So now we're going to work on two agents, just a pair of agents, and just to give you a quick idea here, so we are looking at a specific overcooked AI. I'm sure many of you, if do any AI work, is an environment in which there are two agents, and one, again, is my reinforcement learning agent. I have an agent that is trying to learn from what the opponent wants to do, and the other one, in general, is a cooperative agent. There is some kind of rewards that they get, right, which is relatively simple. But then my other agents could be irrational or can be, again, lazy. And so instead of having just a cooperative agent, I could have an adversarial or a lazy counterpart. So again, when I compute my rewards, they're different depending on the type of agent that I'm with. And of course, when I start, I don't know. I work with you. I don't know if you're going to be lazy or not. I'm sure you are going to be friendly, right? People sitting in the first row are always friendly, right? Because otherwise, people hide. Maybe. Anyway, did you notice this in classes? Same thing happens. Yeah, there's a difference. Students sit in the front row, the students sit in the back. I don't want to say anything bad about people in the back, right? But at the same time, again, there are a lot of things that show aspects of what we do in a kind of a not explicit way, but you can kind of read through. Anyway, so this is kind of a general idea here, and just a kind of high-level ideas here. So there is my agent is a reinforcement learning agent, use the DDPG policy, you can do any other kind of policy. And then there is, again, another agent, and we try to resolve the interactions, and basically, depending if the agent is adversarial or lazy, you update the values. I mean, this doesn't really say too much new, but you keep track, or keep separate alpha and beta value for each type of agent. And this is an example of overcooked AI. Again, it's a kind of a domain is used by many people that do work on reinforcement learning, and so there are different kind of arrangements. So the idea is simple here. There are two cooks, and they cook for some reason they like onions and occasionally tomatoes. There are other things in life maybe you like more, but that's what those agents like. And there are different layout of the space. And the two agents need to get customers' order, put together the order, and deliver. And if they are cooperative, one maybe, picks up the onion, one picks up the other things, and they deliver. The layouts here, again, this shows a little bit of motions, are different in the sense there is different amount of space that the agents have, and slightly different kind of tasks. So again, this is just to give you a general idea. And so again, what we want to do, I have my agent, which is a reinforcement learning agent, trying to learn what the opponent does. And then there is a reward function, which I kind of wrote at the bottom here. Again, depending if the dish is picked up, you get a reward. If there is a soup, you get a reward. If the things are placed in the pot, you get another reward. If it's delivered, you get another reward. So again, this is kind of defined in the systems. And so depending on what you do, you get a reward, and the reward is always what drives the agents. Okay, so again, just to go through quickly, few steps just to make sure if you've never seen this environment. So again, if I have a reinforcement agent, an unknown counterpart, then I update the alpha and beta value after each interactions, and I try to update the value for adversarials or lazy, and take it into account how many times I succeed, how many times I fail. Again, this is alpha and beta values. And At this point, I'll go quickly through a few examples. Not that I want to get into a lot of details, but just to get slightly more specific here. So there are different kinds of the environments you saw earlier, different names. This one is called a cramped room, right? You are in a cheap food place. There's not much space, and there are two agents, right? And they have to work, and they kind of, they can run into each other because there's not much space. The environments here are kind of all discrete environments, so the agents, don't have too much, right? There's a few places where they can be, and they have to make sure that they deliver the order that's coming. So the way we do this, first we do training, because reinforcement learning agent, you have to run for a number of time until you figure out what the opponent is. And this will just show quickly the training. So the examples we have here, we do the interaction with the agent, which 50% of the time is lazy, or an agent 50% of the time is adversarial, or an agent a kind of a mixer. Adversarials or lazy. Of course, you can come up in different ways, and we try to do this kind of more stochastic ways just to see how well it works. We could have done, 100% an agent is lazy or 100% an agent is adversarial. We try to see, well, if it's mixed, makes life a little more difficult, right? Because, I'm working with somebody and say, oh, okay, you did a good job. Now you're not doing a job. Oh, the next step, maybe you do a good job. So it's much more complex. And you see the learning takes quite a bit of time. And what we are comparing, sorry, it's hard to read here. We are comparing our agent called multi-travers. We compare just the travers, which is the system with only one alpha and beta set of alpha and beta values, or a system that doesn't do any alpha and beta, doesn't model the trust. So that's kind of, again, you see it's kind of messy. And then let's just show quickly a few examples. So this is, if you have, in this environment, again, each environment is a little bit different, right? Again, I'll just show a few examples, so hopefully you kind of grab a little more ideas. So if you have in this cramped environment, and if you have fully cooperative agent, the maximum rewards they can get is 187, and those are the rewards that you get over a period of time. So first you do the training, like a reinforcement learning agent learns, and then you do a number of steps. And what it shows here, the kind of orange line is what the agent using multi-travels does, and then the other one is just the reinforcement learning agent, and one is just the travels, which is only one single thing. So it doesn't distinguish if it's lazy or adversarial or not. And as you can see, again, know what the reward for fully cooperative is, kind of gives you an idea. They don't really get the maximum of the rewards. You see, in general, this orange line, which is the multi-travers, does a little better in terms of rewards than the other one. But you see, it's not obvious. And again, the reason is because the agent is stochastic, right? The other agent, again, 50% of the time is lazy, but 50% of the time does the job. So this confuses really the issues, and we're trying to, again, understand how much this confusion really affects the outcomes. And I have a few other similar examples. I'll just go through quickly. This is called the tomato cramp room. You see now there are tomatoes, not just onions. So you want a more interesting soup. And again, the issues are kind of similar, but now if you see the figures on the side, they're a little bit different. And there is a lot of, so the first one, sorry, it's hard to read the figure. The top one is lazy, the second one is adversarial, and the bottom figure is a mix of lazy and adversarial. And you see, again, there is difference, and of course, every time you run, you get some different results, because again, it's stochastic, when it's going to be lazy, when it's going to be adversarial. The performance here is kind of a little more mixed. Again, the maximum reward here is 208, which is, again, is more than what the agents get here. So full cooperation gives you higher reward, and that's always kind of important. And the question is, well, if you are, again, if somebody occasionally is lazy, how much you lose, right? So anytime the opponent, the other agent cannot really be trusted, there is some loss that you make. And the question is try to see how much is the loss. And it's couple more examples, similar idea. So this is called asymmetric advantages. There's a little more space, but there is kind of still a bottleneck in the center. And again, the full rewards here for full cooperative is much higher. Again, so what you see in all these things, the specific values are not especially important. Just trying to give you sort of the intuition. In some cases, makes a big difference. In some cases, it doesn't make a lot of difference. And the last one is called the coordination ring, because there you have the area where the agents work is like a ring, so they can kind of go around instead of simply having to go up and down. And again, in this case, the maximum reward is smaller, and you see similar things. Again, I'm not going to say those results are spectacular, are very important, just to give you the intuition of the kind of things that you can get, again, when you have different types of agents. So just to conclude, because I like really to have time for questions and discussion. So multi-traverse, we think is kind of promising in the sense that allows to recognize more complex behaviors in the other agent as opposed to only say, I trust you or not. So again, you can think of trust as a binary value, yes or no, and here's a more nuanced. How well will this work? In other applications, we don't know. We haven't done it. As I said, this is very new work. I just talked about this at AAAI 2 weeks ago, and of course, the students always finish at the last minute, so she just ran all those experiments there, and then I haven't had much time to try more experiments. So again, this is all fresh area. I want to make sure you all think about, you can do much better than what we've done, right? I'm 100% sure many of you can do better, right? So, and we use Bayesian game theory, and you try to, again, address this way of how the trust affects the choices that the agent makes. And again, in many cases, the performance is not very consistent because, again, there is this stochasticity. Again, think if you have a friend and you can trust a friend all the times. It's very different if you have a friend that, yeah, maybe, yeah, today, yeah, is a good day. You got up on the right side of the bed, so you're helpful. Maybe the next day you're not. Right? It's much harder, right? Even for humans. So again, think about these poor programs that don't have the ability, the richness that we have as humans. So again, there's still a lot of work to be done. And I'm hoping that some of you will pick up this work or similar work, and we really work on trust, which we know is very important, and not just, again, not just for agents, but also human interact with the agent, interacting with systems. So again, there is a lot of potential avenues, and I hope many of you will think about exploring those. Okay?
Thank you very much, Maria. It was a very nice presentation, very interesting. And now it's open for questions. If anybody has a question.
Yeah.
Thank you so much for the presentation. I had a question about, I was looking at the cramped room model, and
Okay, I can go back. Sorry, let's see if I can figure this out. Cramp. The first one or the tomato?
either one. You can go back to the picture. So what I was thinking of in that situation was that maybe that kitchen is only big enough for one person. Maybe the person you're working with realizes that if they do a better job, you'll be out of a job, and they'll be the ones that gets to keep their job. Your reward function would give them the biggest benefit if they did all of their work and your work, and then a month later you would be out of a job. How would you optimize your reward function to make sure that they're not an adversary from working too well?
That's an excellent question. This is something applies to people, right? If you think about an agent or a robot, it doesn't care if it has a job or not, right? But for people, that's very, very important, right? So, when you deal with people, again, that's why trust is important, when done with people, because yes, true, right? Affects your choices are not dependent on what you're doing at the time, but it's kind of long-term thing, right? So you say, I'm losing my job, so let's do this. Agents don't, which is what I like. Programs and robots, they're not as complicated as humans. Humans are very complicated, right? So in this case, again, those agents don't care, right? They're just trying to do the job, and you're just trying to see, again, if you end up having an agent that maybe, again, either intentionally or unintentionally doesn't do the job right, how much can you detect? Because the idea here is, if you detect that the other agent is lazy, you pick up more work. Right? So you still have to deliver and finish the soup. And the question is, can you detect and then come up with a fix for the actions? Good question. Thank you.
Your name is and what department are you with?
My name is Dave Wolofsky, and I'm in the electrical engineering department.
Thank you.
Thank you.
Anybody else, any question or comment?
Thank you. I really enjoyed that. I'm Dave Roberts in the computer science department. So actually, we were talking at breakfast this morning about the increased use of commercially available AI tools, and I think I was listening to your talk and I was thinking a little bit about that conversation about issues of trust there. And I'm wondering, this is obviously really interesting and a great place to start this kind of work with small simulations. But when you introduce humans into these interactions, right, human agents are very complicated and not rational for many reasons. Do you feel like there's opportunity to use a framework like this or an approach like this to help better understand the relationship of trust in human AI interaction?
Yeah, there is a big area, again, if you think about robotics, HRI, human-robot interactions, and people are doing already a lot of work on interactions. A lot of the work is more on safety, because if you're a human and you work with a robot, the main concern, I don't want the robot to run into me, or the robot arm to smash my head or whatever else, right? So safety is the main concern. I don't think people, again, look in a human-robot interaction much to this notion of trust, because, again, we assume that everything that we build is nice, right? It doesn't do bad stuff. The problem, if I have my own robot in a factory and I write the software for them, I make all my robots to be trustworthy, do the right things, they're never lazy. So again, maybe occasionally a robot goes out of whack because, sensor or so. But anytime we have more open systems, and that's why, swarm robotics, multi-agent systems, there's always the potential for some other agents to get into the mix. And that's what we're kind of mostly concerned here. I remember many years ago, I was at some DoD meeting, and maybe 10 years ago, and I was asking, say, well, what about, talking about multi-robot systems, whatever, right? And say, well, what if the robot is an enemy robot? And I still remember a very arrogant answer. No, we are so good, we are the best in the world, this will never happen. Okay, thank you, right? And then, of course, we see that this happens, right? So, again, I think the concern here really is when I think I have control of the systems, but I don't have full control. Or the other issue, again, with robotics, maybe, again, the robot doesn't act properly because of a hardware failure. And here again, I talk with some people at the company in Minnesota, they do aerospace stuff, and I propose this idea. No, we don't need it. We have sensors, so we can check if the robot is defective. I say, okay, good luck. Go with your sensors, right? There's so much trust that our hardware, our software always works. And that's not always the case. So again, I'm interested in this topic, not just because the agent is lazy or so, but there may be, again, some defects, some problems. And this will help us detecting the problems, even if the sensors do not detect it explicitly. So again, to me, on the robotic side, that's really most, again, I understand that it's unlikely that somebody will put a different robot in again, if I have a factory, I don't think anybody will bring in a different robot. It's an enemy, right? You have more tight control. But when you have, again, my robots that go out and clean up the park, what prevents one of you? I made my own robot. And I just going to see. And, often, one thing that computer scientists often like is try to, can I break a system, right? There's not people saying, I'm a bad person. Can I break the system? And then I say, okay, now I try to put my robots that doesn't do the job. And that's possible, right? And I want as much as possible to be able to detect. And then you figure out what to do, right? If I detect this bad robot, maybe again, I don't know. There are different actions I can do. So again, I think there are humans, again, I'm sure many of you know more about humans than I do. And again, it's a very rich area to look into trust. And if you think about now with the large language models, I didn't mention anything here, but this is now the big thing in the AI community, and can I trust my large language models or not? So again, different issues, but trust is always central. And that's why it's kind of funny that it's not been used much in the computing community. Right? There's not been much work on trust. for the computer science community. And that's why I think, again, I like to kind of bring this up. I mean, you don't have to do robots, you don't have to do agents, but try to think about the notion of trust. I think to me, it's very interesting. I'm fascinated by the idea, you know. And I'm sure you'll come up with better ideas than what I have, right? Because younger people always come up with more interesting ideas, right? Thank you. Sure, yeah.
Hi, I'm Jim. I work for iTex. The first question, it seemed to me there was a presumption of zero sum in the amount of work available. What happens if it's not zero sum? Say, for instance, you're running a Kanban system, so the robot who suddenly finds nothing to do can find other things to do, or could possibly be intelligent enough to invent other useful things to do. Where does the model go with that?
So good question, of course. A lot of the game theory work assumes zero-sum games, right? You can do non-zero-sum games that are much more complex. So, no, I mean, I have not thought about that. I mean, this assumes zero-sum, and again, assumes that the more cooperation you have, I mean, the fundamental idea here, you do better if you cooperate with each other. If you trust each other, you do better cooperation. So again, there's a connection between trust and cooperation. But yeah, you open up a new set of problems. Now it's a non-zero-sum games. Absolutely. Lots more work to do. Thanks for the comments. Yeah. Yes.
Thank you for the nice talk. Jishan Guo from computer science. It seems that in your model, you are assuming some kind of smoothness over time for the strategies for these agents. I wonder in some cases where, for example, humans, right, will suddenly get angry and emotional, would this model still work, or could you shed some light on that situation?
Well, that's why I say humans are more difficult, too difficult to deal with, right? That's why we love computers. We control what they do much better, right? So, no, I'm sure there are a lot of other issues that come up when trying to apply this to humans. And that's why I'm saying, no, this is not really an area in which I'm an expert, but there will be lots of open problems there. Again, how do you deal with humans? This again, you know, with agents we have full control. And again, I can make an agent that is lazy, or I can make an agent that occasionally, again, is adversarial. I have full control because I write the software for the agents, right? With humans, you can't really control the humans, right? No, again, which means there is a lot of open problems. Again, what I really wanted to do here is to kind of bring up these issues and get each of you to think about what other problems you can look into that would be good for future. Good questions. Yeah.
Hello, Professor. Thank you for taking the time today. I'm Atharva and I'm a student in the CE department. So I must confess I haven't worked with this environment before. So I just wanted to ask, is it possible to make our own RL agent like 50% lazy or 50% adversarial? Because that's how real life works essentially. So is it possible like you can do that and you'll actually get much more different results than the one you're getting right now?
I'm sure it's possible. Yeah, I mean, we use, in this case, the RL agent, we use the standard policy to train the agent. I mean, there are many more ways, right, of developing RL agents. So yes, you can also, the idea here, you have one that you kind of have control, and then you have the other one which you don't have control, and you try to figure out what the interactions are. And of course, the specific environment is only for two agents, but it's much more interesting to look at multiple agents. So I know I've seen a number of years ago a paper by Henry Christensen and one of his students, maybe 10 years ago, and they were using multiple robots to do a surveillance task. And again, it's used this model, this Travos model. So when a robot, with robots, again, if you have multiple robots, each one has to have a trust value for all the other robots. And when they saw that one of the robots was slow in doing the work, then one of the robots had to pick up the job. So it means that the software of the robots that think they're doing good work has to be capable of saying, okay, now I pick up another task. Again, which is more complex. Again, here again, you are just trying to say, if I have those two agents, one I know and I control completely, and the other one, and just try to see what happens. But yeah, again, there are tons of different things that people can do, and that's why I like this kind of area, right? Lots of space for ideas. Yeah, sure.
Fascinating talk. This is Ali Hajbulway from Civil Engineering Department. I believe the runs that you show 50% lazy or adversarial agent. I wanted to see if you expect to see trends if that percentage changes, because I think this is the hardest. It's really hard to predict, and you have numbers for 0%.
Right.
But when we get to 100%, is it easier for the RL agent to predict that this agent is lazy and maybe get a better?
No, excellent question. We haven't done it yet. I mean, I know my students is running experiments because I said yes. Also, what confuses things here, we are trying to see again, if you have an agent which is not deterministic, what happens? Can you still do reasonably well? But now we're going to do, 100% instead of 50% and just try to see. I'm quite sure it'll be much easier because once you figure out, again, the agent, you want to write the software. Okay, you're a piece of software. I don't trust you because you're always lazy. The values are not going really to change much, right? So the results are going to be much better. But we haven't done it, and that's just kind of next things. Very good question. And next thing you said, we need to try, right? Because you can't just say, okay, this case, right? And then why 50%? Why not 20%? Why not? Again, we're just trying. This is very, very recent work, so, but that will be the next step. We also look like at the maximum reward that you can get, because that's also kind of important, right? I mean, how far are you from the maximum that you can get in the 2R cooperative? And you can say the price to pay to have a partially lazy agent, maybe I do 20% less reward, and maybe there are times maybe it's okay, right? I mean, in the sense, again, I'm not talking about agent and robot. Maybe I have a robot that's not as reliable as some of the other ones, but you can still help me sometimes, maybe better than me alone doing the work, right? Again, so there are a lot of trade-offs that we have to look into. Yeah, good question.
So from here, hello,
Sure.
my name is Alexei Gulyuk, and I'm a teaching professor at material science. So I've got a quick question following one of your slides with the crowded room, I would say. So how do you approach the problem of optimization? Or say you got the room, right? And this room is going to have a certain area. And then you got your agents. Some of them are lazy, some of them are extra productive, right? And how would you approach, let's say you got a big space, right? And you can have X amount of work and you have multiple robots. So how would you approach, or how this function of optimization would look like when you can add like infinite amount of robots, right? But at a certain point they're going to be like impeding each other from working, or it becomes like too expensive to have this many robots in the room. Versus you've got just a few, and it's not enough to cover the entire space. So,
Sure. Now, very good question. We use this Overcook AI because it's a standard benchmark that many people use. I mean, it's not that we decided, we didn't invent this, right? This is a benchmark, the software is out there. So many, many papers now use this Overcook AI. And this is only a pair of agents. And of course, I think we could construct different environments, but if you add another agent, then the software will not work. Exactly. So again, longer term, I like to see multiple agents, because then you can, in fact, I mean, the point you're making, I could say, well, if I have another agent, 3 agents, maybe it can be faster, but if there's not much space, maybe 3 agents run into each other all the time, right? So then you can make this kind of trade-offs. And you need to have more than 2 agents. And we haven't looked at this at all. Again, the paper I've seen for the real robots doing surveillance, I think they had 8 robots there, and a relatively empty space. Again, I didn't put the citation here. It's a paper at least 10 years ago. And then again, they had the agents the robots tried to check with each other, and then when they saw the one area was not covered, they were counting the time, right? The distance between, if you are patrolling an area, and if every 10 minutes you go by, then it's good. If you go by every hour or if you don't go by, then it's not good. So they were kind of counting the time. That's just kind of the metrics they were using. And if an area was not covered, and also a little bit of centralized system, they would say, okay, this area is not covered. And so one of the robots had to decide, okay, I'll go there and cover this area. So again, each layout, each kind of things that you do has to be there different. Again, this overcook is very simple. We use it because a lot of people in the AI community, machine learning, are using this. So we say it's kind of good to use a standard system that lots of people are using. But yeah, I like more agents. I don't like just 2 agents. I mean, it's too boring, right? Multiple agents, you can do different things, right? So that's new work again. So again, hopefully you all see ideas for different things you can think about. They haven't been done yet. So, you know, it's a good topic. Thank you for the suggestions.
Thank you so much. I'm interested in this interaction and what it tells us about learning.
Sure.
So you've got one learning agent and then an agent that does not learn, right? So it's persistently 50% lazy or adversarial.
Yes. Yeah.
And I'm wondering how that might change if you added learning to both agents. So, you know, in human interaction, if you cooperate and I compete and I exploit you, then you learn some things about me, but I'm also learning about you, right? And I could learn 1 of 2 lessons. Oh, she cooperates. If I cooperate, we're both better off. Or, oh, she cooperates, I can exploit her in the future, right? And so, and that would be something that you could program into this as well. Is that something that you've looked into, or is that a next step you've got?
No, it would be the next thing again. We haven't really, again, this is very, very new work, right? And that's why I decided, I also get some suggestions and ideas from you, right? Which I always like, right? So, no, of course, if you have two reinforcement learning agents, you have many different kind of things. So we are trying to start with something very simple. And in fact, this is already, again, because you have this stochasticity, it's already a little bit too complex. Right? I'm going to go back and say, okay, one agent is always lazy. We have kind of baseline to have an idea what happens. But then, yes, you have to extend. Both agents learn, and that gets much more complex. Right? And so, future work for somebody, right? Yeah.
Matt Fox in Entrepreneurship and Innovation.
Okay, sure. Yeah.
So, Mitch Amiano in College of Engineering IT. So that last comment, my word that came into my mind was homeostasis, right? The ability of the body to balance the forces. Another idea that came across my mind while you were talking about the trust as a trait was it kind of extending it far forward is the idea of AI agents having personality, which could then be empirically broken down into a set of traits akin to Hexaco or Big Five or Ocean models, which are ironically maybe, or not so ironically, derived from language studies, right? The LLM coming in there. And so where do you see that kind of into the future? Is this like the forming of a trait theory?
Sure. Yeah. Again, there are a lot of potential things to do. That's why I kind of like, again, I started seeing people talk about trust, and I said, wow, this is so cool. I don't see too much work there, right? And again, I like open spaces. So yeah, of course, I mean, personalities, and some of this is connected with the LLMs, of course, right? Which on their own have their own issues, you know, with hallucinations, how to control. I mean, there's a lot of stuff on the burner. So, you know, I think people who are now students have lots of opportunities. And of course, we don't know the directions really the field is going to take. Some areas will become stronger than others. Now it's like lots of open space. You can think about lots of things. Don't think about too many things, right? Because you can't do, this is again for the students here, you cannot do too many things at the same time, because you spread yourself too thin, right? Your thesis has to be coherent, novel, and focused, right? And then once you become a professor, then you can do whatever you want, right? Then you have much more freedom to do things. But as a student, again, spreading yourself too thin is not a good idea. But yes, I mean, there's a lot to talk about. Artificial general intelligence, is AGI here or not? Right? A lot of people talk about that. Lots of things on the plate. I mean, I think, you know, being in an AI community, we are at a very interesting time. Everybody now knows. When you say, I work in AI, everybody knows. Now, those of us who are older, many years ago, say, I work in AI, say, in what? Oh, artificial intelligence. Oh, okay. Now everybody knows, right? So we are in a good time, but at the same time, there are too many things, too many moving places, moving things. So it's going to be a little bit tricky for everybody, but hopefully some good ideas will come out from this. And all the things you mentioned, absolutely. Again, lots of space for new ideas. So, yeah, good points. Yeah, sure.
Yeah, this is related to what you just said. And I'm one of those students that has way too many ideas to what you're just talking about. I'm just curious to hear a little bit more, even if we just focused on us talking to ChatGPT or any large language model, because I use them all the time, and they're so bad, and there's so much room for improvement, and we can learn so much from psychology and just human interaction. And I think us as humans, we don't even understand all that goes into trust, even the implicit stuff, the stuff behind, the surface. So just curious to hear your ideas of even interacting with LLM like ChatGPT, or what that might look like now or in the near term of how we can make it better or introduce trust, because there's such a gap between us and the guys right now.
No, right. I mean, if you think about it, I think there are kind of two different paths that you can take. One is, and I've seen a talk I was giving recently in Minnesota, you say, well, we're trying to understand how the systems learn. And so she was trying to talk about, pre-training, post-training, are the words different? So you have to go into technical details of some of the open models, because they're the only ones you can really study, and I try to understand what affects the outcomes. So more a system point of view. Or you can take a different approach, which most of the people take, and you kind of look at LLM as a magic box. You don't want to go inside the box and say, how can I use it? And there was a paper written by Rao Kambapati on very short paper, kind of 2 pages paper. I always give to my students to read. And what he said, and I think is a very deep and interesting idea, he said, we are engineers, so we build systems, and we build systems that do what we want. Right? That's our training. Right? Now with LLMs, it's like more natural science. People who do natural science, you don't build your ants or your insects or so, you have to study them. Right? So what he's suggesting, again, you have to kind of use some of the techniques that people in natural sciences uses. Right? Try to experiment, you try to see, but you don't get inside the LLMs. And I think, again, there are 2 different approaches, equally valuable, and hopefully, again, a combination of the 2 things. Again, you try to understand the inside of the system, or just try to use the system and see, how can I use it properly, how can I make it better? So multiple potential paths there.
And we have time for one last question.
Yeah.
Hi, I'm Marla Fedai from Material Science and Engineering. I have a question about, even if this AI model is optimized and then maybe you have multiple agents that is trustworthy, and you use it in the real life applications, such as you gave example of this surveillance and stuff, how do we control them in such a way that even if they do their job as expected, it doesn't actually impede on human agents, such as surveillance-wise? What can it, how can you control it so that it doesn't actually spy on people in a way? Then you say, yeah, this robot is doing its job, but ethic-wise, it might not be doing what it's supposed to do and just maybe stop itself from doing wrong things.
Yeah, very good question. I mean, there are a lot of ethical issues, right? Because anytime we build a system, that's an ethics problem for all AI, right? We build systems, and the system can do bad things, right? I mean, we all know, face recognition, now everybody knows about, right? And often now when you invite papers or conferences, you have to specify if there are any ethical issues that they need to address. So that's still an open question. Now, robots to do surveillance, there was a lot of work, maybe again 10, 15 years ago, there were a lot of algorithms developed using game theory, because, when people again, I don't know if this is surveillance at night in this building. Suppose, again, you have typically the humans go around, it's 10 o'clock, I have to do a tour and check each door of each office, make sure it's locked, right? Then I go back to your room and then repeat this. Are very repeatable, typically. And that's not a good idea. With robots, you can avoid this repeatability because they can be more random. And in fact, there is a lot of work has been done by Bill Tambeni's group, like on airport access control, right? If you have, again, if you know that every day at 10 o'clock, if you enter the airport or this part with your car, there is a guard there checking that you don't have firearms. Now you kind of figure out when it is, and then you go at a different time. So the work in Bill Tambeni is done, again, done for airports, for poaching, for many different things. You put some kind of randomness in the system, which for people is not good, right? I mean, again, suppose your job is to guard the building at night. You don't want each day, okay, 10 o'clock, you have to go there. Now until 3 a.m., don't do anything. Then at 3 a.m., go there, and 10 minutes later, go there, right? The stochastic random things are not good for people, but are much better when you have opponents, right? Because then it's a stochasticity that makes you unpredictable. So there are all these trade-offs, and then you have to decide how to balance things again. So you allow people, and I know that the Bill Tambeni group, they deliver things in some of the parks for detecting poachers, right? And you never have enough guards that can guard the place, but if the guards go around at fixed times, they're wasted. Again, so you need this, but at the same time, again, you cannot have the humans every day, they have very different schedules. So you have to find a kind of compromise, and each application area will have to do that. So again, surveillance a building. I think having robots that go around in buildings at night and check things is a very good idea. Why do you want a person? I mean, maybe you know person needs a job, but why do you want a person to have to stay up at night and do this really boring job? Go around and check the doors, and then if you left your doors unlocked, they put you a sign and say, bad person, make sure your door is locked. I don't know, it's a really good job, right? So, anyway, I mean, you know, the question is, you can have a bad job or no job, and that's a different story. But, you know, if you can avoid jobs that are repetitive and not very interesting, I think robots could do that. But that's kind of, I'm a robotics person, so I like to see robots, you know, doing more things than they're doing now.
Well, thank you very much, Maria. I'm sure that there are lots of questions and comments, but if you have questions and comments, you can either email me and then
I put, sorry, let me just try. I put my email address here at the end. See if I can get there. Yeah.
I might have a couple of questions myself.
So, sure, absolutely. I'm always happy again.
Thank you
happy
so much.
to talk people and do it. Thank you.